Okay, hello everybody. Thank you for joining us today for our webinar entitled Umbilical Design, organized by Egyptian Society of Subsea Engineers with the honor to host JDR to present their own product and give us more insight about the topic. I believe we may have more people coming in later, but we can start. So I would like to invite our speaker, Mr. Angus, to introduce himself first, and then take us for 1 hour session, please.
Okay, thank you very much, Ahmed. So good evening, everyone, and thank you for joining. So my name's Angus Cheen. I'm the Technical Sales Manager at JDR. So I'm a chartered mechanical engineer with around 6 years at JDR, where I've held a number of engineering positions before my current role, which is a combined technical and commercial position where I'm responsible for overseeing our sales of subsea umbilicals and subsea cables. So in terms of the session today, the rough agenda is that we'll start off with a brief introduction to JDR. Because we do only have an hour, I will keep this quite brief, but it's good just to provide a bit of context into who we are and a bit of background into the products that we supply. We'll then go on to umbilical design, where we'll look at the each of the components that comprise an umbilical in detail, and then we'll look at a basic overview of umbilical manufacture and some of the key product groups, and then also we'll round off with looking at how these products are qualified. So this set of slides was originally put together as a training package, so there's quite a lot of detail in some of the slides. So I'll aim to cover the key details as much as possible, and then anything that is uncertain, we should have some time at the end for questions. And also the slides will be distributed afterwards as a reference if required. Okay, so before JDR begin with any presentation or key meeting, we like to start with a safety moment as part of our Think Safety culture. So this is a very brief one, and really it's just particularly focusing on this because many of us are working from home, or at least spending more time in home offices lately. So we really need to think about our desk situation, which may not be ideal, and ensure that we're sitting in a good posture. So please just bear in mind while you're listening to me this evening, and ensure that you're sat in a good posture that won't induce any sort of neck or back pain. So to begin with, a little bit about JDR. So we are a world-class provider of technologies and services that connect the global offshore oil and gas and renewable energy industries. So this covers a range of product lines, including umbilicals, power cables, intervention workover control systems, the subsea equipment as well, and hardware, as well as having an offshore services division that perform the installation and offshore testing and such for our product. We also have an in-house analysis team that can support with feed studies and system analysis and such. So we really do have a vast range of expertise within our company. In terms of our manufacturing locations, so for this particular slide, I am focusing on our umbilical manufacturing locations. We do have other facilities within our group and in different regions. But in terms of our umbilical manufacturing, this is located in Hartlepool, where we've got our large quayside facility, which is particularly suited to long length umbilicals and cables. And on the right here, you'll see one of our layup machines at Hartlepool. This is called our vertical layup machine. So we'll discuss manufacture a little bit more as we go through the slides, but as a basic introduction with this picture, these drums that you see here, each of them has a component on it, and then these are placed onto a large turntable which rotates, and this twists the components together, which are pulled through the top here to form the bundle. And if you look at the two gents down here, you'll notice the sort of scale of the machine here. And then our Littleport facility, we also manufacture umbilicals and cables there. It is a landlocked facility, so the size of the products that we manufacture is more limited. But it also serves us well for the manufacture of our components. So we manufacture our low voltage cables and hoses in-house, which we'll discuss as we go through the slides. So just a little bit more detail on Hartlepool. So as I've said, this is our largest facility, and this is what has really set us up to manufacture multiple large-scale projects simultaneously. So to enable us to do this, we have multiple manufacturing machines. So as well as the vertical layout machine that you saw on the previous slide, we also have this horizontal layout machine here. This is ideal for umbilical manufacture. As you'll note on the previous slide, we had 3 large drums, whereas on this one, we've got a higher number of smaller drums, which is more specific to umbilical manufacture. So we will look at this in a little bit more detail in later parts of the slide. In addition to this, we've also got multiple carousels for storage of product, as well as multiple armoring lines and sheathing lines. At our Littleport facility, again, we've got multiple layout machines. The main layout machine at Littleport is shown on the top right here, where this is another vertical layout machine. But in this case, as you can see, the component drums are on the outside, and the components are actually routed in through the top of the machine and then twisted together and stored in a carousel here. As well as the umbilical cable manufacturing capabilities there, we do also manufacture our hoses and low voltage cables, as I mentioned. So just a couple of headline figures. We're looking at about 22,000 meters of hose per day and about 5,000 meters of cable per day that we can produce. Okay, so after that brief introduction into JDR, I'd now like to go on to the main content for this webinar, which is the umbilical design. So to start with, we have to define what a subsea umbilical is. And it's quite a broad-ranging definition, because the umbilical product is quite broad-ranging, as you'll see as we go through. So an umbilical would be defined as a bundle of cables and conduits that provide hydraulic and electrical power for offshore production systems. And within that, there are a number of components that are listed here, which we will go through one by one within the slides. And there are also some main product groups that I'll highlight some of the key characteristics of these product groups and considerations. So what we'll go through in each of these parts is we'll look at the general construction of the component, and then we'll look at some of the design considerations and things to bear in mind if selecting these components for your umbilical project. So starting off with probably the most common umbilical component, which is a thermoplastic hose. And firstly, you'll see the statement here that it's manufactured and qualified in accordance with ISO 13628-5. So this is the governing standard for umbilical design and manufacture. It's also known by its API equivalent, API 17E. So you'll see this referenced quite a lot throughout the slides. So just to note on that. The hose construction itself is actually quite straightforward. It's got 3 main layers, where we've got the liner, which is the fluid conduit. We then have the braid package, which provides the strength to the hose. And then we have an outer sheath, which is essentially just there to provide some protection to the inner functional layers. And in terms of materials that we may use, we'd be looking at cross-linked polyethylene, XLPE, nylon, or other grades of polyethylene for the liner and outer sheath. And then the braid is made from an aramid fiber, so that would be Kevlar or equivalent other braid. So some of the key input requirements that we would need to design a hose, which should be relatively straightforward, at least for the most part, I think are quite common sense. So we would need to know the working pressure and the nominal bore required for the hose. We also need to know the fluids. So fluids can vary quite significantly between different hose functions and projects. So it's important that we understand the fluids and their operating conditions so that we can review aspects such as compatibility and perhaps the permeability with the liner material. It's also important to look at the project depth in terms of the hose collapse. Operating temperature is also important, and this feeds into compatibility, which we'll lead on to in the next slide. So hoses are generally suitable for temperatures of between -20 to +60 degrees Celsius. So this does cover the vast range of project applications, but not all. And one of the key aspects to consider with temperature is to ensure that the fluid itself is compatible with the hose at that temperature. So quite often compatibility and thermal operation temperature go hand in hand. It's also important to consider if you have a high collapse requirement, that would require additional material, which may increase the cost of the hose as well. And in terms of that also cost, if you have a large bore hose, that means that the manufacturable length of that hose would be less, and you therefore need more splices, which can increase the cost of the hose as well. In terms of the fluid, so I mentioned that compatibility was quite important. Hoses generally are suitable for most standard inhibitors and chemicals that are used for umbilical systems. However, there will be some harsh chemicals that may not be compatible with the hose, but I would certainly note that that is less common. And the final consideration is that within the governing standards for umbilical design, they do state a range for bore size and corresponding pressure. So if you're operating outside this range, you should consider that the design may be more complicated, and there may need to be some bespoke considerations made. So in this table, you'll see that JDR do have qualified outside this range, and so it's certainly not a case that it's not feasible. It just may need some expert guidance on that. So the main alternative to thermoplastic hoses would be a steel tube. And most commonly, the tube material is UNS S32750 super duplex. However, there are other materials that are used depending on the project requirements. So the way that these tubes are manufactured is that the steel tube supplier generally manufactures these in short lengths, around 10 meters long. These are then butt welded together, and then they're coiled onto a layup drum that comes into JDR, and we then put that onto our layup machine and lay it up. So that is the seamless type manufacture, which is most common. However, seam welded tube is also available as well, whereby the sort of straight lengths that are made are much longer as they're manufactured with seam welding, but then those longer lengths are still butt welded together. So essentially you end up with the same butt welds, but a reduced frequency. So in terms of pressure and size, the
Please, Angus, if you can check your connection, because we can't hear you.
In terms of their load bearing capacity, the tubes can actually carry the tensile load required for the umbilical in place of armor wires. So generally the umbilical would be constructed with a layer or two or multiple layers of armor around it, and they're used to pull the umbilical with. So they're the tensile load member, so that you don't introduce strain into the hoses or cables. But in the case of tubes, they're strong enough that they can be used as a tensile member, which means that you may be able to avoid having umbilical armor. In terms of temperature, ideally you want to keep it below 50 degrees Celsius, as otherwise the yield stress needs to be derated. And also, more importantly, there may be a requirement for high temperature coatings, because the tube may introduce crevice corrosion at higher temperatures. And a key consideration is the stiffness. So tubes are by far the stiffest umbilical component, and this can, if you have a large number of tubes or a large bore tube, this can dramatically change the mechanical characteristics of an umbilical, and the high stiffness can increase the complexity of spooling and handling operations and increase the requirements for equipment. And another consideration is that each time the umbilical is bent or handled, the tube will induce a level of plastic strain, and therefore the life cycle of the product needs to be managed within a particular limit to make sure that the accumulated plastic strain isn't too high. So typically a level of 20% is applied, but that really does depend on project requirements. And also the balance of components is important. So if you do have a large bore tube, which would be defined generally as 1.5 inches or larger, then it's key to try and make sure that that's singular and central if possible. As if you have multiple high stiffness components, they're going to throw out the balance of the umbilical, and it may cause the mechanical properties to be uneven and difficulties with manufacture or handling. And the final consideration is a commercial one. So there is a limited supplier base for umbilical tubing. So I've listed the main suppliers here. And what can happen is if the steel tube umbilical market is very buoyant and active, these suppliers can begin to fill up, and therefore the lead times for steel tube can increase significantly. And this can therefore become critical path on your umbilical project and can significantly alter the delivery times that we can achieve for umbilicals. So clearly there's a comparison to be made between steel tube and thermoplastic hose. In terms of pressure requirements, generally hoses are suitable for most applications. There'll be some particularly complex applications where you may need a steel tube, but 9 times out of 10 your hose will be fine. And that's the same for compatibility as well. As I said, it's only really some particularly harsh chemicals where you may need to use a steel tube. In terms of collapse resistance, it may be the case that if you have a deep water application, then you may need to use steel tube, but it would also depend on the fluid that you're carrying as well. A particular consideration is volumetric expansion. So for hoses, when they're pressurized, you're typically looking at between 5 and 15% expansion in the hose. Whereas for steel tube, because of the significantly different material, you get next to no expansion. So with that expansion and increased volume, you end up with potentially having a longer response time if you are, say, actuating a valve at the end of a 10-kilometer, 20-kilometer umbilical. So with steel tube, if response time is critical, it may be the preferred option. And finally, in terms of commercial comparison, so as I just noted, the supply capacity of steel tube suppliers can be an issue. So because hoses are manufactured internally, this means that the lead time and unit cost is considerably better than the equivalent tube. Okay, so moving on to cables. So we're going to start with low voltage cables. And low voltage is defined as anything under 3 kilovolts as per IEC 60502. So generally that's looking at 1 kV or 3 kV cables. And these are most often in pair or quad formation, although other configurations are available. So if you look on the right here, we have a pair cable where we've got 2 conductors, both of them individually insulated. And then we have some sheathing layers, and we also have a screen there, which is made from a copper tape. And typically the size range is around 2.5 to 25 millimeters squared, although we do supply larger low voltage cables. It's just less common. Typically the insulation would be XLPE as well. And in terms of strength member, this may be included depending on the project requirements, and you could either armor the cable or include an armored fiber, which is similar to the braid package we looked at the hoses. So the input requirements and considerations are really quite straightforward for low voltage cables. As you can imagine, we would need to know size and voltage rating and the conductor configuration. What is also important is to understand if there are any signal transmission requirements. As we can, although we have standard cables, we can also design to meet these requirements by adjusting the construction of the cable if there is particular signal requirements. In terms of considerations, these again are quite straightforward. So the cables are suitable for operation up to 90 degrees Celsius and generally aren't the limiting component. In terms of the length, it's worth considering that if you have a large conductor, you're going to reduce the manufacturable length and therefore more splices and more cost. And therefore, if you need a large low voltage conductor, it may be worth considering switching to a higher voltage, which leads on to the next slide. So we're looking at medium and high voltage power cores. So when we say medium voltage, this would be anything between 3 kV and 33 kV. And then higher voltage is anything above 33 kV. So generally that would be up to 66 kV, which we're beginning to see emerging in umbilical technology, but most often umbilical power cores are within the medium voltage range. So usually it's a 3-phase system where you'll have 3 cores, although there can be examples where there's more than that. But if we consider a 3-phase system, you would have 3 cores like on the right here. You'd have a water block conductor, then you have a triple extrusion layer. So this is where the additional complexity of the design comes in comparison to the low voltage cable. So you have a triple extrusion. And then we have a metallic screen and an outer sheath as well. So typically the size range for medium voltage cores or these sort of power cores, we're looking at between 35 millimeters squared to 630. That's not an exclusive range. That's just what we generally see. Okay, so going on to the key input requirements. So it's important for us to know the operating voltage and also the load that's going to be transmitted. The conductor size, if it is known, is also important for us to be advised. But if that's not known, then we can calculate the required conductor size based on the operating voltage and the power or load. However, it is quite common that we get inquiries where the load or the current that's required to be transmitted isn't provided. And that really is an important input in order to assess whether the cable itself is actually fit for the project requirements. It's also important to know that the earth or the short circuit rating, as this can also affect some of the aspects of the cable design, in particularly with the screen itself. So some of the considerations for selecting these components. So voltage drop is an important consideration. It's not something that affects JDR as such, but we understand that it's a key consideration for our clients. So typically we understand there's a maximum of 5% allowable. The voltage rating is also important because this drives the insulation thickness. And also the current requirement is important because this drives the conductor size. And to explain why this is important, we can look at some top level and basic electrical equations. So if we consider ohms and the power law, so if we consider P equals IV, so the power, which we know is constant because we need to provide a certain power transmission. That's why the cable is being requested. And therefore, if we increase the voltage by, say, if we operate at 30 kV instead of 10 kV, therefore we reduce our current. So going back to this consideration here, we can see that by increasing the voltage, we can actually reduce the current and therefore reduce our conductor size. And because the conductor is the majority of the metal within the core, that reduces the cost considerably. And that's why there is such a drive within industry, and in particular you'll see in the offshore wind industry, to operate at higher and higher voltages, because it really does improve efficiency overall. And to add to that, if you look at the power loss equation here, this is exponentially related to the current. So as we reduce the current and therefore the conductor size by increasing voltage, we reduce our losses as well. So it really does help efficiency. And finally in this slide, so in terms of the temperature, the cores are suitable for operation at up to 90 degrees Celsius, but the main consideration there is that when they're operating, carrying this sort of load, they may cause heating of other components, which is generally the limitation, where your hose may be suitable for 60 degrees Celsius. So you would have to limit the performance of the power core. So the final component that we're going to look at briefly is fiber optic cables. So these are constructed as shown on the right here. So you've got a number of optical fibers, glass optical fibers. So you could have up to 96 in one cable. These are supported within a stainless steel tube, which is filled with a gel to support them and seal. You then have a layer of sheathing and armor that basically just provides protection to the inner fibers. So the fibers could be provided in single or multi-mode, but the most common specification that we see for umbilicals is ITU G652D. And that's certainly not the only specification that can be supplied, but it's just the most common one that is used for umbilicals. In terms of considerations for selecting the component, it's aside from the standard specification, we'd also need to know if there are particular transmission requirements such as attenuation or such. And it's also worth noting, because we can have up to 96 fibers within one cable, whether instead of having 3 cables, you could combine them all into one. And just finally on this, so I've noted a few times about if you have a larger component, it reduces the manufacturable length, and therefore you need more splices. So a splice is where where we have a long project umbilical length, and we need to have splices of the individual components in order to achieve the overall umbilical length. So at JDR, we've got qualified splices for all of our internal components here. Okay, so I'm just going to touch briefly on umbilical manufacture and talk through a little bit more of what I showed at the beginning on some of the earlier slides. So the umbilical bundle is constructed whereby the umbilical components are packed onto drums, and these are then helically laid together at a set pitch. So when I say helically, that would be either clockwise or anti-clockwise in one full direction. Whereas there is also an alternative method called oscillatory or ESSE lay, it's known as, whereby the lay direction changes from clockwise to anti-clockwise. But for the purpose of this slide, we're going to focus on the helical lay. So I'm just going to show you a brief video to demonstrate this. So if you see here, you can see all the components. Let's pause it here. You can see the components laid onto the drums here, which then the whole machine spins around. And these components could be steel tubes or fillers, as are shown here. And you'll see from this slide, so the whole machine spins around and the components are routed through the machine and down into this lay plate here where they're twisted together on the left. There you see a steel tube being helically laid up. And there you see the bundle of components. So you can see the steel tubes, and those are filler ropes next to it as well. Okay, so depending on the number of components within the umbilical, you may have multiple passes, and this is where the number of drum locations on the machine the number of components exceed the number of drums on the machine. So the way that you get around that is that you manufacture one pass with however many components you can fit. You would then pass that back through the machine and lay the second pass of components around that. As I've noted, when we were looking at the bundle before, you may include fillers, so they could be rope or extruded fillers. And they're there really to keep the bundle circular and to distribute the load. So I mentioned armoring earlier in the slides. So this is helically applied on a specific armoring machine. So it could be a single layer or multiple layer, which is shown here. So in this case, you've got a left hand and a right hand lay of armor. So that's to make sure that it's torque balanced. And then once you've assembled your components, you've armored it, then you apply the outer layer. So this could be the polyethylene sheath, as is shown in the picture on the right, or it could also be polypropylene roving string, which is very commonly used for cables. So this really is there to provide protection to the components. So you have an inner sheath which protects the components when they're being armored. Then you have the outer sheath, which protects the overall umbilical from external forces. So going on to look at some of the main product groups. So in this section, we'll talk through production umbilicals. So these could be providing subsea control, platform control, or they could be infield or tiebacks for redevelopments, which we're seeing much more commonly now in industry. And also a particular subgroup of these umbilicals are subsea isolation valve, SSIV umbilicals. So these are used to operate the fail-safe valve that shuts off pipeline supply to the platform in the case of an emergency. We'll also briefly look at subsea power cables. So these are used for transmitting power from platform to platform or from shore to platform. And also they can be used for providing subsea power, such as ESP pumps. And also consideration is steel tube power umbilicals. So this is a hybrid product combining aspects of production umbilicals and subsea power cables together to drive improved efficiency, which is one of the driving influences in industry at the minute. Another important consideration in terms of product groups is static or dynamic. So static umbilicals, which are most common, are where you may have a platform and the umbilical is routed through a J-tube, or if you have a fixed subsea connection where the umbilical is not expected to move. Whereas a dynamic umbilical would be a floating connection, such as an FPSO or floating platform that's, for example, shown on the right in this picture here. So for these sort of applications, it's important to consider the high fatigue that is imparted on the umbilical and the components. So just to briefly look at some examples of production umbilicals. So the production umbilicals covers a vast range. It's the overarching group for most umbilicals. So the typical characteristics are quite wide. They can include just about any sort of component. Typically, it would be hose or steel tubes combined with low voltage cables, and they may also include fiber optics for telecommunication purposes. The length can vary significantly depending on project requirements. I've stated up to about 100 kilometers here. Really, it just depends on the vessel storage capacity as to what the maximum limitation would be. And they may or may not have armor. SSIV umbilicals, they are routed through a platform J-tube to the subsea termination typically. Because they perform a limited function in terms of operating and controlling the valve, they have a limited number of components as well. So you've got a low number of hoses and low voltage power cables, as in this example you'll see on the right here, and they typically wouldn't include fiber optics. And because of the proximity of the platform to the shut-off valve, they're typically quite short length as well. And as you'll see in this example here, it's got a high number of armor layers. This is because with such a lightweight bundle, it's often important to add additional weight through the armor to ensure that it's stable on the seabed. So there's some key design considerations here. I'm not going to read through all of these. I'm going to highlight some of the key ones that apply to most umbilicals. So the size is obviously very important. The bigger the umbilical, generally, the more expensive it's going to be, or at least it can increase other costs such as installation. So we should always try and ensure that the diameter is kept as small as possible, whilst considering design rules and such. So I noted before that stiff components should be distributed as evenly as possible, such as the tubes, to ensure that the bundle is balanced. Another consideration for tubes is that the weld cap of the tubes may impact on other tubes if neighbored next to each other, so it needs to be considered for certain sizes. In terms of fillers, there's an example here showing the difference between a shaped filler and a rope filler. So the shaped filler is providing some structure and supporting these hoses here, whereas the rope filler is generally just filling the outer space here. So in terms of the outer layer, it's a good consideration is that instead of using extruded sheath as mentioned here, if it's possible for project requirements, it is much cheaper to use an outer roving, which is generally used on cables, and in my opinion it's not used enough for umbilicals, so that's certainly a good consideration to have. In terms of the dynamic applications, we as the JDR need to ensure that when we're designing that the component lay angles, so the pitch that they're wound together on the machine, is sufficiently high to ensure that we don't have strain buildup. So if you can imagine that there's quite a long pitch length where the change from compression to tension region is quite spread out, you could, in a particular section, when it's subjected to dynamic motion, introduce quite a large bit of strain buildup. Whereas if you have a high lay angle, this compression and tension is equalized and changed much more frequently, so that the buildup is much more limited, and therefore it manages the high fatigue application. So going on to subsea power cables. So typically a subsea power cable looks like this on the right here. So we have 3 cores with a single fiber optic. However, for applications such as subsea ESP pumps, it may have multiple triads, such as shown on the right here. So some considerations for subsea cables for design are the thermal analysis in the J-tube. So this is the highest temperature section of the cable and is the most common limitation of the current rating. So that's what's going to limit how much power you can transmit through your cable. Most commonly is the J-tube, because when it's on the seabed, even though that's the majority of the route, the temperature is much lower. So it's not a limiting factor, whereas the J-tube limits how the cable can perform. So it's really important to focus in on that during the analysis. Another key component, key consideration is coil ability. So if we have a single armor cable design, because of the triad manufacture, this can actually be coiled in a basket without the use of a powered carousel turntable. So that greatly increases the storage options for vessels and for us as a manufacturer. And another consideration is the lay pitch. So if we look at these examples here, you'll notice that the triad of cores are always positioned equally from each other, and also a set distance from the center. And this is to ensure that the length of the cables are exactly the same, to ensure that you don't have one phase of the power system that's longer than the other, and therefore you would end up with an electrical imbalance. So finally, in terms of the product group, so I'll touch on steel tube power umbilicals. So an example of one is shown on the right here, where we have a combination of steel tube and power functionality, as well as other signal components as well. So the considerations are very similar to what we discussed already for production umbilicals, with some important additions. So the heating effect of the power cores may compromise the performance limit of steel tubes. So as I mentioned earlier, they're suitable for up to 50 degrees Celsius. And above that, you may need to introduce coating. So the thermal analysis is very important for hybrid steel tube umbilicals. Additionally to that, the electrical magnetic effects of having a three-phase system in a bundle with a number of metallic components can also result in there being induced electrical effects, induced voltages in those components. So it's very important to perform an electromagnetic analysis as well as a thermal analysis to assess the level of these electrical effects and whether any mitigations would be required. So you've seen, as we've gone through these slides, albeit quite quickly, as a top level overview, but there's a vast range of components that can go into an umbilical, which can produce a vast range of product types. And therefore, I think quite an important question to answer is how do we qualify this product, and how do we avoid having to qualify it repeatedly when the umbilical components or designs are rarely the same between projects. So the way that we do this is by utilizing a qualified design envelope. So where a product has been qualified with a similar umbilical, so it may have the same type of components within it, that product could be fully qualified. And therefore, if you have a similar future design which has slightly different components but generally the same design, then that would also be covered as it's within the design envelope. And then in addition to that, you would have manufacturer acceptance testing to verify that the product is fit for purpose. And by not performing qualification, it doesn't mean that you don't want to do any testing. It may be that you want to characterize particular mechanical properties of the umbilical through project verification testing on a sample. So in terms of umbilical, the qualification is as listed here for ISO. And what we would recommend is that this isn't repeated, except if you're looking at a completely new design or something that's outside of existing technology. Otherwise, if you want to have a certain project test data, you should consider what is applicable and what adds value. So commonly that would be the tests listed here, which you may, if you have any background in this area, you'll see that these are the sort of tests that would drive inputs for tensioners and sort of rock dumping and installation spread parameters. So it means that you can get accurate data to the installation contractor rather than using design calculated methods. And in terms of power cable qualification, the umbilical qualification is quite extensive and onerous, but the power cable is even more so. And that fact, together with the fact that cables are much more similar than the variation you get in umbilicals, means that the approach taken by industry is to qualify a particular size and voltage, and then anything less than that size or voltage is therefore covered within that design envelope. So that would be done for each of the standards. So for 33 kV medium voltage, you'd be looking at IEC 60502 and SIGRA. For 66 kV, it would be IEC 60840 and SIGRA. So each of those would have a qualified design envelope. And within that, they would cover the range of alternatives you may find. Okay, so just to round off the presentation we've went through, I just wanted to summarize some of the points that I've mentioned and some of the suggestions I would make in terms of key aspects to consider for cost reduction and optimization should you be involved with any umbilical scopes in the future. So as a general rule, you should use hoses where sufficient for project requirements. So as I've mentioned a number of times in the slide, they are suitable for the vast majority of projects. So it's only really for high complexity applications where you would need to look at using steel tubes. You may want to consider using multiple smaller bore lines rather than large bore lines, as it's generally lower cost overall, although I know it does depend on flow rate. You should also look to combine cable functions if possible, as the lower number of components means fewer passes on the layout machine, which means less cost. And typically, a number to have in mind would be about 16 components per pass through a layout machine. As I mentioned on the medium and high voltage power cores, utilize higher voltages for power transmission wherever possible. And that means that you can optimize the core size and reduce your project costs. You should also look to optimize stability. So the armor wire is generally sized according to seabed stability requirements. So if we perform detailed analysis and use very accurate met ocean and soil and root data, that means that we can potentially reduce, or even if we're considering a steel tube umbilical, remove the armor. So that can save significant cost and also reduce the weight of the umbilical, which may save on transportation costs. We should also avoid inclusion of unnecessary components. So an example of that is Teredo worm protection tape, which is an outdated requirement. Where the project has multiple umbilicals, consider whether you may be able to utilize common designs across that, as that can yield manufacturing efficiency benefits. And finally, look to utilize qualified designs wherever possible. Although there may be some benefit in performing project-specific testing, we certainly wouldn't advise performing full-scale requalification unless there's a significant design change or it's pushing the boundaries of existing technology. Okay, so thank you everyone for your time listening. Apologies if I was quite quick going over any points, but I believe we've now got some time for questions.
Thank you very much, Angus. I think you can open the chat box. You have some very good questions waiting you. Do you hear me? Okay, Angus, do you hear me?
Angus, can you hear us?
Sorry, Ahmed, I can't hear you in case you are speaking. I'm not sure if it's an issue at my end.
Can you hear us?
I think it's on your end. If you could open the chat box, you can find the questions.
Okay, so I guess if I read through the questions and I'll answer them one by one. So what is the capability of the vertical and horizontal layout machines in terms of the number of elements in the umbilical bundle? Also in terms of the max lengths of cables inside the umbilical without splicing. So the number of elements in the umbilical is generally around 16, as I noted, but for the vertical layout machine, it's more efficient if we have less than 6, because we can have 3 very large components as is suited for cable manufacture. And then the max lengths of cables without splicing, that really depends on the particular size of the cable itself. So if the cable is larger, then that reduces the length that we can achieve, and it's really limited by how much you can fit on a drum. Okay, so a good question. In case using armor wire layers, what is JDR's precautions to avoid hydrogen generation from the galvanized steel wire armors? So it is an issue that has been raised in industry. Generally, the protection that we advise is present is that although some corrosion will occur with the armor wires when submerged in water for the design life, as they're bonded at both ends, it should be reduced. But more importantly, because the armor wires are provided with an outer covering, this should limit the circulation of seawater across the galvanized wire. So even if there was a sort of top layer of corrosion that occurred, this should very quickly be maximized, and therefore you wouldn't have a situation where you have a high level of hydrogen production over a long time. And that is the case even if there was a damage to the outer sheath, it would be limited to a particular section. What is the facility capacity in terms of umbilical length that could be manufactured in one length, assuming umbilical OD is around 150 millimeters? So for that sort of size, the limitation would be our carousel capacity. I mean, I wouldn't know the number off the top of my head, but we would be looking at somewhere between probably 70 to 100 kilometers would be the maximum that we could do in that length. But there are also options if it was longer, but it would certainly be enough to cover the vast majority of project layouts. Okay, please say the acronyms for electrical cable covering when you can. Okay, so we're looking at high density polyethylene for the outer sheath, or it could be in terms of insulation material for medium voltage, that's cross-linked polyethylene. For low voltage, it's also cross-linked polyethylene. albeit a medium voltage. What we use is a water-tree retardant material for that. What is the technology used to get water block conductors? So the way that is achieved is during the conductor manufacture. So when it's being stranded, you apply a powder to the conductor strands, and therefore that provides longitudinal water blocking within the conductors. And so this is really a requirement that's present for medium power cores. And the conductor water blocking essentially limits the transfer, the travel of water should the umbilical or cable be damaged to that sort of level, and means that the repair can be achieved. Could you tell us some challenges you faced during the manufacturing process? Yeah, so I think one of the challenges is efficiency. So when we are changing components during the layup, it's important to ensure that this is efficient as possible. So down to even the fillers, everything needs to be highly efficient in order to improve our output. Another challenge that is present is for steel tube umbilicals. If you have large bore tubes, their stiffness is a significant magnitude higher than most umbilicals on their own. So the layup of those components poses a challenge in terms of handling them to ensure that it's done safely and without damage to the product itself. Are the cable splices qualified for water and gas blocking? So the cables, the splices themselves essentially reinstate the cables exactly as per the virgin cable itself. So the conductor and such is manufactured in a way that the existing properties are present. What is the required qualification testing or inspection required to reuse a subsea bundle after project lifetime, say 20 to 25 years? So after that sort of design life, that would be around the that would be at probably around the top level of design life. It's the typical design life that we would supply umbilicals to. So it's not certainly the maximum, but it's what we would generally supply them to. So at that sort of period, it is probably becoming a consideration as whether it is still fit for purpose. So what we would suggest is performing a level of testing similar to what is done sort of pre-installation or at factory acceptance, and that should, because the test pressures would be above the operating pressure, that should, assuming it was successful, evidence that it was fit for purpose. And that is the sort of thing that JDR could assist with if you wish to get in contact with me. My email is at the bottom there. Do you have a case study for cutting and retrieval of subsea cables? I'm not sure if we have a case study as such, but we will have experience of that, and it is something that is occasionally done in abandonment scenarios. Potentially, if there's poor weather, then you may have to cut the product, abandon it, and then retrieve it at a later date and return with the installation. Okay, I read somewhere that 80% of offshore wind failures are due to the cables. What is done for scour protection? I'm not sure in particular in scour protection. I would say that that's not a particular area of expertise of mine. But I think I've never seen that a particular figure of 80%. I think it's as with any new market, there's a number of challenges that are facing the offshore wind industry, and whether that's with the cable requirements or whether that's with the sort of the overall turbine construction, there are challenges. And I think the difference when we consider wind farm production, sort of power transmission, when we consider oil and gas systems between platforms, the main difference is that wind farms, the cables are generally operated to their absolute limits, if not in excess of their actual capacity, which can lead to some issues. Whereas for generally for oil and gas systems, the cables are usually operating at a decent level below their maximum, and so the issues that are apparent are less common. And I see the next point, which I suspected may be the case, but I hope everyone's still able to hear me, is that my headset isn't working. So let me just check if I can fix that.
Do you hear us now? I'm speaking to test your speaker. Do you hear us? Okay, now you're connected. Do you hear us well?
Okay. Okay, just saw another message in the chat box. My point is to reuse the Subsea bundles without retrieval onshore. I couldn't find the specific standards or guidelines for qualifications of Subsea bundle. Okay, yeah, I mean, we can certainly look into that. A lot of the offshore work that's done in terms of abandonment as such is considering that you wouldn't have to retrieve it onshore, as it obviously introduces a large amount of cost and delay into the schedule. It would depend on the product in question, but most of the testing could be performed on the vessel. But certainly, yes, please get in touch and we can discuss further.
I think, Angus, you have answered most of the questions. I really enjoyed this 60 minutes talk. I believe our participants also have the same feeling. I would like to thank you personally for your effort yesterday and today. I hope you hear me now.
Yes, no problem. Also, thank you very much.
Great. Also would like to thank our participants who joined, and I would like to also to ask everyone to follow our page on LinkedIn, also to share our updates with their networks. Maybe our next webinars will be of interest to you or your friends. So keep the wheel coming, and keep the momentum. I see the same old faces attending they attend mainly all our webinars, so that's good. We need to increase our audience, and this can only happen by your help. So thank you once again, everyone, and thank you, Angus, and thank you to JDR as well.
Yeah, thank you very much for the opportunity to present, and everyone who's wrote in. Yeah, please get in touch with my email there if anything we can assist with.
Yeah, and hopefully we can have another talk by yourself.
Yes, yeah, exactly. Just yeah, give me a call and we'll go through it.
Yeah, perfect. Okay, thank you, everybody. We will end this session now. We'll be having this recorded on our YouTube channel, so you can also share it. Maybe in 2 days it will be available, hopefully. Thank you, everyone.
Okay, great. Thank you, everyone. Have a good evening.
Thank you.